This is the memory map section of the MIPS software training course. The MIPS Privileged Resource Architecture divides the memory map into segments that can be accessed in two basic modes, kernel mode and user mode. The idea is to separate memory so the OS and its resources are protected from user programs. In kernel mode, all addresses are available. There are different memory mappings depending on the state of the system and if you have a TLB or fixed mapping MMU. We're going to start with the most common map, the map of virtual memory after the boot process has completed. Here is a picture of the virtual memory map. The first thing to note is all program addresses for both the kernel and user modes are virtual addresses. Also, all addresses are in hexadecimal. On a MIPS 32 core, the memory map covers a 4 GB range of physical memory. The lower segment of memory, KUSEG, covers a 2 GB virtual address range starting at 0. It can be cached and mapped using the TLB to anywhere in physical memory. This segment can be accessed in kernel or user mode. The next two sections, KSEG 0 and KSEG 1, are designed to be used for the OS code and data. These segments can only be accessed in kernel mode. If the processor is in user mode, any access to the kernel segment will cause an address error. Both KSEG 0 and KSEG 1 segments are directly translated to the same lower 512 megabytes of physical memory. For example, address 80 million and A0 million are directly mapped to physical address 0. The difference between the two is KSEG 0 addresses are cacheable and can be used once the cache has been initialized. KSEG 1 addresses are non-cacheable and are used at boot time and for memory map I/O. The next two segments cover the virtual address range that runs contiguously from C0 million to FFFFFFF and is accessible only in kernel mode. The region is divided into two halves called KSEG 2 and KSEG 3. KSEG 2 was designed to be accessed to programs running in supervisor mode, but supervisor mode is seldom used, if ever. An OS such as Linux concatenates these segments together and refers to this as kernel high memory. You may choose to use a fixed memory translation. For FMT, the memory translation is not dynamic but static. Instead of just KSEG 0 and KSEG 1 being mapped to a specific physical location, all virtual addresses are mapped to specific physical locations. The kernel and user segment is mapped to physical memory starting at 40 million. The two kernel segments, KSEG 1 and KSEG 0, are always fixed mapped to the lower 512 megabytes of physical memory. The two high memory kernel segments are directly mapped to physical memory. There is an inaccessible 512 megabyte physical memory address starting at 20 million. This is the memory map at boot time before the cache or TLB is initialized or when an NMI or cache error exception occurs. The boot code must be in KSEG 1, which is always fixed mapped to the lower 512 megabytes of physical memory. This segment contains the boot exception vector BF C00000, which is where the CPU will start fetching instructions at power up or reset. Once the cache has been initialized, the code can execute from KSEG 0, which will access the same lower 512 megabytes of memory through the cache. The kernel can also access the lower 2 gigabytes of virtual memory, which always directly maps to the lower 2 gigabytes of physical memory. This segment is also uncached. KSEG 2 and 3 will be mapped through the TLB. Note, on an NMI, all exception vectors revert back to their cold boot locations within your boot ROM. So the TLB refills will use page tables set up for booting, not the page tables that the OS was using. At this point, you can see the virtual address 0, 80 million, and A0 million all point to physical address 0. This is an example to give you a perspective of the MIPS core map in relation to a system memory map. This system has 128 megabytes of SD-RAM starting at physical address 0. As you can see, this maps to virtual address 80 million in KSEG 0 and A0 million in KSEG 1 to physical address 0. The exception vectors are located in this region starting at address 0. There is an optional 128 megabytes in the next contiguous memory region. There is a monitor flash that holds the system monitor, for example, Yaman or U-Boot. On this system, the designer created an alias on the bus of the first megabyte of the flash starting at physical address of 1FC00000. The internal system and device registers are located at physical address 1F million, which is mapped to KSEG 0 address of 9F million and a KSEG 1 address of BF million. At boot time, before the code clears the ERL bit, the kernel user segment is directly mapped to physical memory. The remaining addresses in the system physical memory are unused. Any accesses to these areas will result in a bus error.